Okay. Good evening. I am Saurabh and I welcome all of you to this live session for the NPTEL course Advanced Thermodynamics and Combustion. This is our second live session, and in this session we will be focusing on the content of week 2. We will try to solve some problems, and I hope these problems will be helpful for you to clarify some concepts, and you will also get idea how to solve the assignment problems. So if you have any doubt in the lectures, that you can ask. If you have no doubt, then we will proceed. So have you any questions, or should we proceed? In the last session, we had some discussion, like someone asked that why we are again and again referring to this term hydrostatic system, and what exactly is hydrostatic system. So this is the content directly from the lecture itself. So it clearly defines what a hydrostatic system is. So it says that any isotropic system. So isotropic basically means that system is independent of properties. Independent of direction. In all the directions, the properties are same. Okay, so you can also say it is homogeneous. Okay, so it says that a isotropic system of constant mass and composition that exerts a uniform hydrostatic pressure to the surrounding is referred as hydrostatic system. Okay, so the key point here is that it exerts a uniform hydrostatic pressure to its surrounding, and it is in the absence of gravity, electricity, and magnetism. The PVT system is often encountered because it is a simple hydrodynamic system. Okay, and there can be several categories under this hydrodynamic system. So, okay. Okay, sorry for the interruption. Uh, so there can be pure substances which have a single chemical compound. Okay, so for example, H2O. So H2O can be in the liquid form of the or in the solid form as ice, or it can be in the vapor form, but the composition is the same. It is H2O. There can be homogeneous mixture of different compounds. Okay, for example, you can have a mixture of oxygen and nitrogen. Okay, there can be heterogeneous mixtures of different gases, and there can be also some liquid particles. So all these systems are hydrostatic system. In many textbooks, we use this term, a simple compressible system. Okay, so a system is this is from Singer and Bowles books. Okay, so I'm just reading this paragraph so that we can appreciate the fact that in the context of this course, this simple compressible system and this hydrostatic system, both are similar. They are equivalent, at least in the context of whatever systems we are discussing in this course. Okay, the system is called simple compressible system in the absence of electrical, magnetic, gravitational, motion, or surface tension effects. These effects are due to external force fields and are negligible for most engineering problems. Otherwise, an additional property needs to be specified for each effect that is significant. Okay, so why we are discussing all these things? We discussed in the last session that how many independent properties are required to fix the state of a system. Okay, we discussed Gibbs phase rule. Okay, for example, for a simple compressible system, for a hydrostatic system, we need only two properties, and the third property can be calculated from the remaining two. Okay, for example, if you have pressure and volume, you can calculate the temperature from state equation. Okay, that state equation can be ideal gas equation, or that can be something modified version, for example, van der Waal equation. Okay, so from state of equation of state, you can calculate the remaining property from the given properties. For a simple compressible system, the independent properties can be only two, and the third will be dependent on the remaining two. Okay. If there are, other force fields, for example, if there is gravity, or if there is, magnetism, or something else, then for that particular, force field, you will require another property. Okay. So in a simple compressible system where we have only two, independent properties, in those type of systems, these sort of force fields are absent. External force fields are absent. Okay. If the gravitational effects are to be considered, for example, the elevation Z need to be specified in addition to the two properties necessary to fix the state. Okay. So I hope that you are getting the point. What is, why we are stressing so much about this simple compressible system or hydrostatic system, or this Gibbs phase rule, because we just want to stress on the fact that for a simple compressible system, uh, for a hydrostatic system, we need only two properties. Third property can be calculated. Okay. And so you should not get confused by this particular term, hydrostatic system. Somewhere you can find this term called simple compressible system. So both are, equivalent in the context of this particular course, or the systems encountered in this particular course. Okay. So I hope that clarifies any doubt related to this particular term, hydrostatic system. Okay. So someone asked in the previous session that why we are referring this term again and again. Okay. So when we say this term, that means we are inherently assuming that these external force fields are absent. Okay. Anyways. Now, if there is any doubt, you can ask, or we will start with the problems that we have in this assignment.
Good evening, sir.
Good
This
evening.
is Adarsh.
Hi,
Actually, I
Adarsh.
could join. Yeah, just now only I could join. I
Okay, no
had
problem.
only asked this doubt.
Okay.
But you had
So,
clarified it before.
okay, so I should repeat that.
Just 2-3 sentences, if you can, it would be helpful.
Okay. Well, what we just discussed was that you I think you asked that why we are using this term again and again, hydrostatic system. I think what you might have thought about the hydrostatic system is like a water filled, a tank filled with the water, or some dam like that, right? But in this context, in the context of this course, this hydrostatic system simply means a simple compressible system. Okay. And the definition itself says that any isotropic system, isotropic means that the properties are independent of direction. Okay. So you go in any direction, you will find the same properties. Okay. So a isotropic system, that means it is independent of direction, of constant mass and composition. Okay. So composition means the chemistry, or, chemical, composition is not changing. Exerts a uniform hydrostatic pressure to the surrounding is referred as hydrostatic system. And external force fields like gravity, electricity, magnetism, surface tension, all these things are absent. Okay. So when we have this type of system, then how many independent properties we will require? We will require only two independent properties to define the state of the system. Okay. The remaining properties can be calculated from these two properties. These two properties can be pressure and volume. Then temperature you can calculate from these two properties. This can be pressure and temperature. Then you can calculate volume from these two properties using the equation of state. Okay. That equation of state can be your ideal gas equation, or it can be some, more uh, complex or more modified version. For example, van der Waal equation of state. Okay. So in this course, we have used this hydrostatic system, but you might be familiar with some other term. For example, simple compressible system. Okay. So this particular part I am showing from the book by Sinjal and Bowles. Okay. So very famous book. I hope that you are familiar with this book, and many of you might have also read this book. Okay. So in this book, this term is used called simple compressible system. Okay. So I will just read this paragraph. So state postulate. So a state postulate basically says that a state of a simple compressible system is completely specified by two independent intensive properties. Okay, so intensive properties, what are intensive properties? Intensive properties, don't depend on the size of the system. Okay, right? Intensive properties, I hope you know. If you don't know, then we can discuss. A system is called simple compressible system in the absence of these external force fields: electrical, magnetic field, gravitational field, motion, right? For example, if you have motion, some acceleration, then you will add some pseudo forces. Okay, surface tension effects. So all these effects are absent in the case of simple compressible system. So if any of this force field is present, so these effects are due to external force field and negligible for most engineering problems. Otherwise, if any of these field is present, then we will need an additional property. So one additional property needs to be specified for each effect. Okay, for example, if you have gravity, then you will require one more property, right? So for a simple compressible system, we said that we require only two properties. But if you add one more external field, for example, gravity, then you will require one more independent variable. Okay. For example, if the gravitational force or effects are are to be considered, then elevation Z need to be specified. Okay. So that Z, is another independent property. Okay. So simple compressible system and this hydrostatic system. So both of these terms basically refer to the same thing, at least in the context of this current course. Okay. So whatever systems we will consider in this course, in the context of those systems, we can either use the simple compressible system, this term, or you can also use the word hydrostatic system. Okay. So the purpose was to, stress on the fact that you need only two independent properties, and the remaining properties can be calculated because they are dependent on these two independent properties. Okay. So if you add something else, any other, force field, then you will need more independent properties. Okay. In the previous session, we also discussed something called Gibbs phase rule, right? So if there are more phase, then, uh, if you add one more phase, then independent property will be reduced by one, right? Okay. So that's what this hydrostatic system mean. Okay. So this is similar to what you might have studied in your basic thermodynamic course as simple compressible system. Okay. So is that clear?
Yeah, yes, sir. Thank you, thank you.
Okay. Okay. So next we were just starting this assignment, or you have any more questions in the lectures or in the assignment that we can discuss, or we will proceed with what we have in this, problem set.
Yes, sir.
Mhm.
Like in this assignment that were given, I think as assignment number 2,
Okay.
this is this particular question, number 9,
Particular question number.
said that find the change in entropy, number 9.
Okay. Okay. So I think I just checked that question and answer section. So someone has already raised this doubt that in question number 9 and 10, the exact question is not given. They are just asking find the change in entropy or something like that, but they have not, specified what change, right? So that's what you are saying, right?
Yes,
Yes,
sir.
sir. Actually, data is not given in that problem.
Data is not
Proper
given.
data is, yeah.
Data is not given. So I think someone has already raised that doubt. So I hope that that will be, addressed. Okay. So
Okay.
so that will be addressed by NPTEL team, I hope. Okay, NPTEL team or the other TAs. Okay, so if it is not addressed, then you can just solve the remaining questions. That those two questions you can ignore. Okay, what is the last date of submission of that particular assignment?
It's 5 of this month, sir.
5 of this
It's
month,
tomorrow.
tomorrow. Oh my God.
Mm.
You please, submit the remaining questions. So for question number 9 and 10, they will try to address.
But I think that's Puran Singh this side.
That is,
Sir, I think myself Puran Singh.
uh-huh.
So I think that those questions, whatever is given, that is work assignment 0 only. So, so that those marks will not be considered, I think.
What is 0? I couldn't hear you properly.
Is it audible, sir?
You are audible, but I couldn't.
Sir, actually,
You said something that it is
I
0
actually
or
said
will
that
not.
whatever assignment, that is a 0 assignment, I think. It's not assignment 1 and 2. So I think, so that
No, it is
what
assignment 2. Someone is saying that it is assignment 2. Second assignment probably.
yes, I remember that that is assignment 0. So those marks will
No,
not
it
be
is
considered
assignment
for.
2.
It is
No,
assignment
it
2.
is assignment 2.
Question number
Yes.
9 and 10.
Oh, okay.
Assignment 2.
Yes, it is
Okay.
assignment 2, right? I can say. Find the change in entropy of the body with the appropriate sign in kilojoule per kg Kelvin. And 10 question is find the change in entropy of heat engine. So yes, the data is not given. You're right. So you please submit, solve other questions and submit it. And that will be, addressed, I hope. Okay. So other questions you have no doubt, right? So we can proceed with these questions for, of this session. Okay. So question number 1, it says that the work done in all reversible paths between the exact same initial and final equilibrium states is identical. So this statement is true or false? Hello.
I think it's true, sir.
It is true. Work done we are saying, right? Work done in all reversible paths between the same initial and final equilibrium states. Is that identical? Hello.
Yes, sir. It's true, I think. Because that is
Okay.
calculated through the curve, area curve of the PV diagram.
You are very close. You said that work done between any two states is area under this curve. Okay. For example, we can make the PV diagram or entropy temperature diagram or any, these sort of diagrams. For example, this is point A and this is point 2. Then work done between point A to point 1 and point 2. Okay. So this is path A, let us say, a reversible path A. And another path can be path B, right? This can be path B. So area under both curves is different, no? Area is not same.
Yes, yes.
So since area is different, so the work done along both of these paths will be different, right? So that is why we call that this work is path dependent quantity. Okay. Work is path dependent. Correct. So along different
Sir,
revolution paths, the work done will be different. Okay. So this is false, not correct.
oh, sir,
Uh-huh.
like here in this, they said that in the reversible path, I think,
Uh-huh.
isn't it talking about the return or reverse in the exact same path to the initial step?
Actually, there can be multiple reversible paths connecting two points. Okay. So what I think you are thinking like that between two equilibrium points there will be a unique reversible path. So it is not true. Okay. So between two initial, I mean, you have one initial and one final equilibrium states. So between those 2 points, you can have multiple reversible paths. Okay. And along each of that path, work will be different. Okay.
Exactly.
I think I am getting what you are trying to convey. Uh, but I hope you understood what I
Yeah,
am
I get
trying
it.
to explain.
I am
Mhm,
clear with it.
mhm.
Yes.
You can just, I mean, from the figure itself, it is very clear, and you can also, make different paths. The work, heat, heat is also path dependent, right? And few quantities which define the state. Okay, those quantities are path independent. Those quantities we call properties, right? For example, internal energy, pressure, volume, temperature, entropy. All these things are path independent. So these are also called point functions. And work and heat, both of these are path dependent, and these are called path functions. Okay. So that's why this statement is false. In the lecture, when we try to prove the Clausius inequality and we discuss about generalized force and displacement field. Okay. So in that particular context, you might have the confusion, but in general, the work and heat, both of these are path functions. Okay. Now coming
Sir,
to the
in
next.
the,
Huh?
sir, in the last question, it mentioned that equilibrium state.
Equilibrium state. Okay.
Uh, so for the work to be the path function,
Mhm.
it should not be it should be equilibrium state, or it's not to be equilibrium state. The question, it should be equilibrium state or not.
Okay. So there are few things we should keep in mind. Number one, you said equilibrium. Okay. So equilibrium state, when we say state, that means we have fixed the coordinates. Okay. We have fixed the volume, pressure, temperature, all these things. Okay. And system is in equilibrium. And when we say system is in equilibrium, we basically means thermodynamic equilibrium. And at equilibrium state, there are no gradients.
Property will not change.
Properties, there will be no gradients. Okay. So equilibrium state, when we say this equilibrium, so this word equilibrium, this term equilibrium is associated with state. Okay. Equilibrium is associated with state. When you change the state, for example, in this case, you have changed the state from point 1 to point 2. Then in order to change the state, you will have to follow some path. Okay. You want to go from point 1 to point 2, you will change the path. Okay. And that path will be consisted of many points. Okay. On each path, there are many points. Okay. Here, you have many points. Okay. So if all the points consisting of these paths are in equilibrium, okay, if all the points which make this path are in equilibrium, then we say that this process is reversible. Okay, because all the states which comes during the change of these states, if all these points are in equilibrium, then we say, okay, this is reversible process. Okay, quasi-static equilibrium. But if it is not in equilibrium, then there will be some irreversibilities, right? So
So, sir, if
what was your question? So work and heat, they are path dependent. Okay. So both work and heat, they depend on path. Okay. And that path can be reversible or it can be irreversible. Okay. So in both the cases, the work and heat both can be calculated. Okay. But they will depend on the path.
yes, sir. So, sir, if in any process, if properties are changing, so that it will not applicable for that process.
In any path, the properties will change. Okay. Because it is path. What is path? Path is, connecting between two states.
Yes, sir.
And when we say properties are basically state functions. Okay, they are defining the state. So if you change the state, properties will change. Properties, we want to reserve this term property for the path. Sorry, state functions, the point functions. Okay, so if you change the state, properties will change.
So
Work
this
and heat
statement holds true
or
or
work.
not?
So this is false.
No, no. For the change of the process, this will hold or not?
Which process? For
No,
this particular
any process,
reversible path?
any process.
Yes, for any process. So this is saying that there are several reversible paths which can connect these two states. Okay, there are two states. Okay, first is initial and another is final. Okay, so one is our initial and two is our final. So there can be several paths, right? Several reversible paths, and it is saying that along all the reversible paths, the work done will be same. So this is not correct, right? Because you can connect these 2 points using many different ways. Okay, many reversible paths, and along each different path, work and heat, these interactions can be different, right? Because work is
Yes,
anyway area under the curve, and if you
yes, sir.
change
I
the curve,
got the question
uh,
and I got your point.
right,
But if the process is happening,
process is happening. Okay,
is this statement is true or not? Hold or not? Means the work is still, if the process is going on, the work is still on the depend on the path or not?
process is happening, so there is some path. Okay, that path will be representative of that process. Okay,
Yes, sir.
and work will be there, right? Work will be there. That can be zero. Okay, that can be zero, but work will be defined along that path. For example, if there is some process in which volume is not changing, isochoric process we call them, then work is zero. Okay, but in general, if there is any process, so associated with that process, there will be a path, and associated with that path, you can calculate the work.
Okay, sir. Okay, sir. We can move ahead, sir.
And that process can be anything. That can be reversible, that can be irreversible. Okay,
Okay, sir. Okay, sir.
so the work done when we go from point A to point 1 to point 2, the work done can be anything. Okay, so if you go through this path A, work will be, let us say, WA. If you go from through the path B, then the work can be WB, and they may not be equal. Okay, they can be different. Okay, but if you are asked what will be the entropy changed when we go from point 1 to point 2, then entropy change will be same along all the paths. Okay, internal energy change along all the paths will be same, because these internal energy, pressure, volume, temperature, entropy, enthalpy, all these things are dependent on only the initial and final points. Okay.
Sir, I have one doubt here.
Uh-huh.
Yes, you were mentioning about that irrespective of reversible or irreversible, the heat and the work is path dependent only. Is that?
Yes.
Yes. So means this irreversible means is it for the just cover confusion this all means all reversible path like that, or means since the already that system is in equilibrium state, then how this reversibility and irreversibility will come in the picture? Just can you
Okay, sure. So it may happen that initial state and final state, they are in equilibrium. Okay, state A, initial state that we are calling 1. So in that state, system can be in equilibrium. Okay.
Okay.
Now system is brought in final state, state 2. In state 2 also system can be in the equilibrium. Okay. But in between state 1 and state 2, system can be in equilibrium or cannot be in equilibrium. Okay. It may happen.
Correct.
Okay. So if system always remain in equilibrium when we move from point state 1 to state 2, if all the time, if the system remain in the equilibrium, then it is reversible. Okay. But if at any point this equilibrium is lost, okay, then system is irreversible. Sorry, the path is irreversible.
Okay. Okay.
Okay. So
Um,
if it is asked that work done in, so if it is asked that work done along all paths, you forget this term irreversible. The work done along all the paths between the exact same initial and final equilibrium state, you also remove this equilibrium state. The work
Okay.
done along all the paths between exact same initial and final states, that can be different. Okay. The path can be reversible, path can be irreversible, but work and these heat interactions, they will be dependent on path. Okay.
Okay.
Because here it is very clear. Okay, from the diagram itself, we have studied that the work done is, PdV, area under the PV curve, and you can see that along different path, the area under the curve is different.
Okay, sir.
Okay. Now coming to the next question. It is saying Clausius theorem states that for a reversible cycle, the cyclic integral of dq by t is
Equal to
Huh?
zero.
Zero.
Oh, no.
Zero.
yes, it is 0. Okay. And for irreversible,
Some generation will be there.
will be for a irreversible cycle. For reversible cycle, it is 0. And what about irreversible cycle?
Less than zero.
Will be
Less than zero.
less than 0, negative. Correct. Okay. So in general, the cyclic integral of dq by t, that can be either 0 or less than 0. Okay. So this is Clausius inequality. Okay. Okay. Now coming to the next question, it says that why two adiabatic lines cannot intersect on the generalized work diagram. You just neglect this term generalized work diagram just to not get confused. Let us say a PV diagram. Okay. That can be a PV diagram. Work diagram can be your PV diagram, or it can be TS diagram. Okay. So on such diagrams, why two adiabatic lines cannot intersect? Can they intersect or not? First question is this. Okay. Can they intersect or not? For example, this is a PV diagram.
So it
And,
will not intersect.
and this is, let us say, one adiabatic path. Okay. So this is this is adiabatic line. Okay. And if I draw another line B and I say that line B is also adiabatic. So is it possible?
It will not, sir. I think it will not.
And why it is not possible?
If two lines are adiabatic lines, then it will slope will be same, sir. I think the slope will be same.
Slope is dependent on point, first of all. Okay. For example, if you try to find the slope at this point, here slope is something else. Okay. Here slope is something else. Okay. And if you find the slope here slope is something else. Right? Okay. The slope depend on the point. But at a fixed point, slope is fixed. Okay. The slope is dependent on point, on the state. And at a given state, at a given point, the slope is same. Okay. So for example, at the intersection point, if let us say these intersect, then at this intersection point, both of these lines are having different slopes, right? So this line will have this slope. Okay. And this another line has this another slope, right? But at a given point, the adiabatic process or the adiabatic line will have a fixed slope. Okay. So at a given point, there cannot be two slopes for a adiabatic process. Okay. So this is not possible. Correct?
So for adiabatic line,
For a, okay, at this point, if you say, okay, I will start moving adiabatically, then you will have to follow a certain slope. Okay. There cannot be two slopes at a given state. Okay. Because
yes,
what is the equation of adiabatic process? Mathematically also you can prove. Okay. Adiabatic process is, PV to the power gamma is constant. Okay. Right?
yes, sir.
So at a given point, you have P1 and V1. Okay. So what you have? You have that constant C1 is equal to P1 V1 to the power gamma. Okay. So from that, through that point, the equation of adiabatic line will be PV to the power gamma is equal to P1 V1 to the power gamma. Okay. Okay.
Okay, sir.
It is like X times Y to the power some constant is equal to some other constant. Okay. So if you have an equation, you will have a curve. Okay.
Yes, sir.
Right?
Right, sir.
And what is the slope? If someone asks you to calculate the slope of this adiabatic process, how will you calculate the slope? What will be the slope of this adiabatic process? How will we proceed?
Gamma times of minus P by V
Gamma
times of minus P by V
times
minus P by V.
minus P by V. Okay. And how do we find that if I forget this? What is
You
slope for this
differentiate
curve? What is the slope of
differentiate
the slope is dy by dx. Okay. So just differentiate this equation. So what you will have is, first you differentiate with respect to P, you will have dP times V to the power gamma, plus then you differentiate with respect to V, then you will have gamma P times V to the power gamma minus 1 is equal to 0. Okay. So you have dP times V to the power gamma is equal to minus gamma P V to the power gamma minus 1. Right. So sorry, यहाँ पर एक dv भी होगा ना, times dv. Okay, times dv. So you have dp by dv is equal to minus gamma p v to the power gamma minus 1 divided by v to the power gamma, and that becomes dp by dv is equal to minus gamma p by v. Okay, so that's what you told. Correct. Okay, this is slope. Okay, so for any process you can find, okay, you have a equation. Okay, you have an equation in the form of this function y, some function of x comma y is equal to 0. You just differentiate that, okay, and you will get the slope.
Sir, this intersecting of lines, I mean the intersecting of processes is only for the adiabatic or is for the all process?
For any process in which we have this type of equation, okay, we have x to the power y, sorry, x times y to the power some constant. Okay, so this gamma is not changing, first of all. Okay, that can have different values. For example, gamma can have value 1.33 or gamma can be like 1.4 or something. Okay, so once you fix the gamma, so this gamma is need not to be the ratios of specific heats. Okay, in the case of adiabatic process, this is the ratio of specific heat, but you said if it is not adiabatic, then this gamma will be something else. Okay, not the specific heats ratios. Okay, but you will have this fixed equation. Okay, so once you have equation, you will have a fixed path, right? Correct.
Yes, sir.
Because whenever you have this type of equation, x times y to the power some constant, let us say some constant is gamma. I will not use gamma. Let us say k is equal to c. Then what you have? You have y to the power k is equal to c by x, or you have y is equal to c by x to the power 1 by k. Okay, so you put one value of x, you will get a one value of y, right? At least in this particular case,
Yes, sir.
right? So for each given x, you will get one given value of y. Okay, so you will, trace a single path. Okay, one more point I would like to mention here is that
So, sir, it will intersect or not, sir?
not intersect. For this, if for this type of things, it will not intersect.
No, other than the adiabatic.
Other than the adiabatic will also not intersect if the gamma is constant. Okay, so okay, y is equal to x to the p to the power, pv gamma to the power 1.33 and pv to the power gamma, sorry, p times v to the power 1.33 and p into v to the power 1.5. Okay, these two lines can intersect with each other. Okay, these two lines can intersect with each other. Okay, but if you fix this thing, then you will get one single curve, right? So this particular curve, and this particular curve, they can intersect with each other. I should write very explicitly. So pv to the power 1.33 is equal to some constant k, and pv to the power 1.5 is equal to k2. Okay, so these two curves can intersect each other. Okay, for example, at a given point, okay, so this I should insert one page. So at a given point in the PV diagram, so this is PV and this is a point A, and if this is a adiabatic curve, okay, this is a adiabatic curve, then you can have an isothermal curve. Okay, so adiabatic and isothermal, they can intersect. Okay,
Yes,
right?
sir.
Adiabatic and isothermal, they can intersect. So this is, let us say, isothermal, and this is adiabatic. So they can intersect each other, but through one given point, only one adiabatic curve can pass. Through one given point, only one isothermal curve can pass. Okay, this is possible. Correct?
Yes, sir. What do you mean by given one point?
This one given point, this one given point, this given point. ये जो बनाया लाल.
Okay, sir. Okay, sir.
Okay. So if through one given point, only one adiabatic curve can pass. Okay. So all the adiabatic curves through that point will be, superimposed on each other. They will not be different. They are essentially the same. If
They will coincide. Okay, sir. They will coincide.
They will coincide. If they are not coinciding, that means through a single point, they are passing many adiabatic curves. That is not possible. Right? So through one given point, only one single adiabatic curve can pass. Through a given point, single isothermal curve can pass. Okay. Is that clear?
Yes, sir. Clear, sir.
Now just moving away from thermodynamics. If two curves are intersecting, okay, you can have a mathematical equation for intersecting curves. Okay, that will have some different mathematical form. Okay, but the equations of this form, which have x times y to the power some constant, some positive constant, okay, 1.33, 1.5 like that, and it's equal to some other positive constant. So these type of equations, they will not intersect. Okay, if the gamma and c are constant. Okay, I'm just mentioning this thing explicitly, that two intersecting lines can have a single mathematical equation. Okay, ठीक है ना?
So two same mathematical.
Just let me reframe this thing. I mean, if you have two intersecting curves, okay, this type of curves, you can still have a function like this, f x comma y is equal to some constant. Okay, but in that case, one given value of x will produce two values of y. Okay, but I should not confuse you here. Okay, but I hope that is you got what I meant.
Yes, sir. Yes, sir.
I mean, two intersecting
Sir,
lines.
Instead of sir doing this, well, we are taking the help of mathematics, sir. So we can directly tell that how these two processes are same two processes are intersecting in a device. If we assume
Same
that
two
if there
processes
is a
will not intersect. Two adiabatic curves will not intersect. Two isothermal curves will not intersect. That's why I was not bringing this mathematics, because that will require separate discussion. But you get the point why they will not intersect, right?
yes, sir. Yes, okay.
Because at a given point the slope is fixed. If the slope is fixed, then you will get only single curve. If they are two intersecting curves, that means both of those curves will have different slope value at that given point. Okay, two intersecting curve will have different slope values at the intersecting point. Okay, but you cannot have two slope values at a given single point. Okay, so that there will be contradiction. Correct? Fine.
Yeah, sir. Yeah, one last question regarding the last topic, sir.
Hello.
Yes, sir. Sir, making this the process are intersecting each other. We are bringing such concept for the discussion. Is there any significance, sir, of this? Not we are studying that two processes are not intersecting each other.
Okay. So there are two things. I will repeat again. If two curves intersect each other at a given point, then at that given point, both of those curves will have different slopes. Okay. But a given process, for example, adiabatic process, will have a single slope value at a given point. Okay. So the adiabatic process will have a single slope value at a given point, but two intersecting curves will have two different, slope values. So both are, not matching. They are contradicting. Now coming to your point, what is the significance of, this fact that they are not intersecting? So the so if you want to, let us say, calculate the entropy change along two paths. Okay, I am given one example. So you have two paths, point A and point B. So what you can do is you can connect these 2 points using one, let us say, isothermal process and one adiabatic process. Okay. Hello.
Yes, sir.
You have 2 points, point 1 and point 2, and there is some random process. There's some random process between point 1 and point 2, and you are asked that you have to calculate the entropy change along this path. Okay, entropy change, yani ki S2 minus S1, this you have to calculate. But you know that entropy is a point function, so you need not to follow this path. What you can do is you can make one isothermal curve and one adiabatic curve. Okay, so what you can do is you can make one isothermal curve, okay, passing through point A. This is isothermal curve, and then you can make one adiabatic curve passing through point 2. Okay, so this is adiabatic curve, this is isothermal curve. Okay, now what you get is you get this path you can get. Okay, I said initially it is along isothermal, then along adiabatic. So let us say this is point 3. Okay, so the path becomes 1, 3, 2. Okay, so if you can calculate the entropy change along path 1 to 3, then 3 to 2. So along that path, the entropy change will be equal to the entropy change along this, random path. Okay, is that clear? When the process is adiabatic, dq is 0, right? No heat transfer.
Right, sir. Right, sir.
Okay, and along the isothermal path, what is heat transfer between point 1 and point 3, that you can calculate. Okay, and at this isothermal path, the T will be constant. Okay, T will be constant. So whatever heat change is between point 1 and point 3, heat interaction between point 1 and point 3 divided by the temperature along this, isothermal path, that will be the entropy change along point 1 to point 3, right? From point A to point 3, this will be entropy change, and along adiabatic there is no heat interaction, so entropy change will be 0. Correct? So you can easily calculate the entropy change. So this is one example, but this is useful in many other ways as well. So that's what it signifies. Okay, so it is quite relevant. Also, when you try to prove the cyclic, for the cyclic case, the Clausius inequality, you use many, Carnot cycles. Okay, so there also these things are, underlying assumptions and underlying concepts behind those things. Okay, but I hope you got what this question intended to explain. Okay.
Okay.
Okay, so I hope all these things are clear, and if there is any doubt, we can discuss more. Otherwise, we can move to the next question. Okay, I hope it is fine. So question 4, it says which quantity is path dependent. So now it is very easy. We have discussed in this in quite detail. Internal energy, is this path dependent? No. Entropy change between two equilibrium states, again, no, we just discussed. Heat transfer is path dependent, yes. Enthalpy is not path dependent. So option C, heat transfer is path dependent. Okay, very easy. Okay. Now,
Yes, sir.
moving,
Okay.
moving to the next question, question number 5. We have to tell whether this thing is true or not. While the path dependent infinitesimal reversible heat transfer dq r means reversible, is an inexact differential. Okay, it is an inexact differential. Dividing it by the absolute temperature T transforms it into an exact differential representing a state function. Is that correct?
Yes, sir. I think it's talking about entropy and it's correct, sir.
So it is true, but you should have a clear understanding of these terms: exact differential, inexact differential, all these things. So are these things, I mean, you are comfortable with these terms? If you are, then we can proceed or we can discuss these terms. All the thermodynamic properties,
Aware of
they are,
this.
they
Aware
are
of
state
this.
functions, they are point functions, they have exact differentials. But the quantities which are not state functions, those which are path functions, they don't have exact differentials. They are inexact difference. They have inexact differentials. Okay.
Yes, sir. Understood. Understood.
And what is the condition for a differential to be exact? For example, you have certain quantity z that depends on x and y. If you write dz is equal to something times dx, some function, that function can be function of x and y. Okay, this is function of x and y plus another function that is also the function of x and y times dy. So if this function is exact, then what will be the conditions? I mean, how will we check that whether this z has exact differential or not? Okay, so z is certain quantity that depends on x and y. Okay, and dz is the differential of z. So whether this differential is exact or not exact, how will you check?
So dou m by dou y at a constant y.
Yes, del m by del y at constant x, that should be equal to del n by del x at constant y, right?
Right, sir.
And in the previous session, I also said that you should make yourself comfortable. You should, convince yourself about this particular, check for a differential to be exact or not exact using some, paths. Okay, you can take 2 points, point A, point 2, point A and point B, and you can have, different paths for going from point A to point B. And if this condition is followed, then you will find that change in that particular property along both of these paths is same if this particular property is followed. If this particular property is not followed, then the change in that particular, variable, that property will be different along different paths. Okay, that you can check yourself. Okay. Okay. Now coming to the next question, question number 6. It says that the mathematical statement of the inequality of Clausius for an internally irreversible cycle states that the cyclic integral of this dq by t must be strictly less than 0, right? Correct? We have discussed this thing. Cyclic integral of dq by t is negative for irreversible process. And for reversible process, this dq by t, not process, cycle actually. Okay, anyway, we have written this cyclic integral symbol. So that itself means that the process is acyclic. Okay. Now coming to the next question. Question number 7. It says that a system undergoes a complete cyclic process where the cyclic integral of the state changes is mathematically cyclic integral of ds is equal to 0. Yet the Clausius integral yields dq by t, its cyclic integral is less than 0. And it is saying that it is an apparent mathematical contradiction. And you have to explain this. It is saying that cyclic integral of ds is 0 for all processes, cyclic processes. Okay, but cyclic symbol we have already written, but this del q by this del t, this can be negative for irreversible processes. Okay, so for irreversible processes, this cyclic integral of ds is 0, but the cyclic integral of dq by t for irreversible process, this is less than 0. So is this a contradiction or what?
It doesn't seem any contradiction.
Huh?
It doesn't seem any contradiction.
Yes, there is no contradiction, right? Because both of these are, different quantities. Okay. For reversible processes, ds will be equal to dq by t, but for irreversible processes, it is not true. There is no contradiction. Question number 8 says, which of the following conditions definitively implies an irreversible non-adiabatic process? Non-adiabatic process where heat flows out of the system. Okay, so we have an irreversible and non-adiabatic process. Where heat flows out of the system. So del Q, it is negative. So let us see all the options one by one. Option A says reversible isentropic. So this is not correct, right? Because in the question itself, it is written that it is a irreversible, right? Irreversible process. But it is saying reversible isentropic, so this is not correct, right? Option B is saying irreversible isentropic process. Now let us see this option. Irreversible, isentropic. So irreversible means entropy change of the system is zero. Oh, sorry.
Not equal to 0.
Entropy change of the system is not equal to 0. There is some entropy change. No. Again, sorry. Isentropic means entropy change of the system is 0. Okay. Isentropic means entropy change of the system is 0. Irreversible means entropy generation is there. Okay. And irreversible means there is some entropy generation. Okay. Hello.
Yes. L is yes, sir.
So there is some entropy generation, but total change of entropy of the system is 0. So that means some entropy will be, flushed out from the system with the heat. Okay. If there is some entropy generation, because process is irreversible, but it is isentropic. So total entropy change is 0. Okay. So whatever amount of entropy has been generated, that should be reduced, that should go out as the form of heat. Okay. So that amount of heat will have to go out. Okay. So if both of these things are happening, irreversible plus isentropic, so that will mean that some amount of heat will have to go out. Okay. Right. Some heat will have to go out from the system. Is it right? Some heat will have to go out from the system so that entropy can also go out with this heat from the system. Okay.
Right, sir.
And since heat is going out, so that means it is non-adiabatic. Okay. And it is already written in the option itself that it is irreversible. Okay. So irreversible plus isentropic means irreversible plus non-adiabatic. Right. So irreversible plus isentropic definitely implies that process has to be irreversible non-adiabatic. Okay. So option B, which says irreversible isentropic, that definitely implies that process has to be irreversible non-adiabatic. So option B is correct. Other options, if you see, they are not correct. Reversible adiabatic, this is not correct. Irreversible adiabatic, again not correct, because if it is irreversible and adiabatic, then the entropy of system will increase. Okay. But if the system entropy of the system increases, then the processes will no longer be isentropic. Okay. So one point I would like to highlight here is that a isentropic process simply means the entropy change of the system is 0. But isentropic processes can also be irreversible. Okay. There can be some processes which are irreversible, and because of that irreversibility, some amount of entropy will be generated. And if heat is going out from the system in such a way that the exact amount of entropy that is going out from the system associated with the heat is exactly equal to the entropy generated because of irreversibility, in that case, the total entropy change can be 0. Okay. So the process will be isentropic, but it is also irreversible. Okay. So a isentropic process can be irreversible. Okay. This you should keep in mind. But usually when we say that, let us consider a isentropic device or isentropic, compressor or turbine like that, then usually we assume that process is reversible. Okay. So there are two things. One is concept and context. Okay. You should understand this concept that a isentropic process can be irreversible, but sometimes you will simply see this word written isentropic device like that. Okay. Then you should, in that particular context, it will be clear that you have to consider the process to be reversible. Okay. So both things you should, be comfortable. Okay. Right. So the context will clarify whether you have to consider a reversible or irreversible process. But in general, conceptually, an isentropic process can also be irreversible. Okay. I hope that is clear. Okay.
So the given all processes are adiabatic, sir.
Given
all processes are adiabatic in the question.
in the question, the process is given to be non-adiabatic, right?
No, in the options, all the processes are adiabatic. I am asking all the processes are adiabatic.
No, option B, it is not adiabatic. Some heat is going out from the system, right? ये क्वेश्चन क्लियर है ना? सेकंड ऑप्शन जो कह रहा है, ये कह रहा है कि प्रोसेस irreversible है और isentropic है. Irreversible means some entropy is generated, but isentropic है, then entropy change should be zero. But entropy is generated, but still the entropy change is zero. That means some entropy is going out. How the entropy will go out? Entropy will go out with the heat. Okay, so the heat will have to go out. And if the heat is going out, then how the process can be adiabatic? Heat transfer is there. Right?
Okay, sir.
Okay. Reversible isentropic processes are adiabatic. Okay. Option A, if you see that is adiabatic, but option B, it is not adiabatic.
Sir, CDs are CDs.
In the CD, it is clearly written that it is adiabatic, reversible adiabatic, irreversible adiabatic. Only option A and B, it is not written whether it is adiabatic or not adiabatic. You have to imply from whatever information is given in the option. In the options, it is giving it is isentropic or it is reversible or not reversible. So for option B, it is irreversible. That means some entropy is generated. But isentropic means entropy change has to be zero. So that means some entropy has to be go out so that you can have zero entropy change. If entropy is going out, that means it will have to go out with the heat. So heat will go out, then it is not adiabatic. Okay. So it implies that it is irreversible, non-adiabatic. Okay.
Sir, the second name of the adiabatic process is isentropic.
No. No, it is not. If you are an adiabatic process, that simply means that there is no heat transfer. But if there are internal irreversibilities, then entropy can increase and that process will no longer be isentropic. Okay. So usually we assume, in the questions, for example, it is written that consider an isentropic turbine, isentropic compressor. Then we assume that there is no heat transfer. Okay, we assume that there is no heat transfer. It is reversibly adiabatic. We assume that it is reversibly adiabatic. But in general, when we say isentropic, that does not mean that process has to be adiabatic. Okay, so that's what I am saying. I am saying there are two things. One is concept. Concept is that isentropic does not mean that process has to be adiabatic. But context will make you clear that whether you have to consider it a reversible adiabatic or not. Okay.
So, sir, why not the option D, sir?
Why not option D? Irreversible adiabatic. You understood the question, what it is saying. Question is saying that which of the option will lead to an irreversible non-adiabatic. Let us see option 4. Okay. Option 4 is saying irreversible. Option 4 is saying irreversible first of all. So that means entropy generation is zero. but
Yes,
it
sir.
is also adiabatic, so there will be no heat transfer, right? So irreversible means there is some entropy generation, but there is no entropy transfer between system and surrounding. So the entropy of system will increase, right?
Right, sir.
Entropy of the system will increase. So, okay, fine. But the option should imply this whole information. Irreversible, non-adiabatic. Can you read this thing? It is saying irreversible, non-adiabatic. But if option 4 is clearly saying that it is irreversible adiabatic, then how will be it non-adiabatic? I mean, I hope this is clear, right?
Yes, sir. But in the option
Option
D,
4
sir,
is clearly saying it is adiabatic, but your question is saying that process should be non-adiabatic. Then how the option D can be correct? Correct?
Okay, sir. Okay, sir.
So isentropic processes isentropic process, these can be reversible plus adiabatic or irreversible plus non-adiabatic. And in the non-adiabatic case, heat transfer will be from the system to the surrounding. Okay. So the isentropic processes can either be reversible adiabatic or irreversible non-adiabatic. Okay. In the second case, the heat will go out from the system to the surrounding. Okay. So isentropic processes can have both of these conditions. Okay. But usually if the question says that process is isentropic, then usually we assume that process is reversible adiabatic, right? In turbine and compressors, we assume that process is irreversible adiabatic, but it can be any of these two. Okay. So that's why I said the context will make it clear. Okay.
Sir, the irreversibility of the process doesn't make the adiabatic process non-adiabatic.
Does adiabatic and isentropicity both are two different things. Okay. So
So
isentropic process can
the
hello?
irreversibility of the adiabatic process doesn't make it the non-adiabatic.
No. Adiabatic simply means that there is no heat transfer. There can be irreversibilities inside the system. Okay. You just consider this water bottle. Okay. You just consider this water bottle and assume this is perfectly insulated. Okay. Just assume this is perfectly insulated. There is no heat transfer. And if you shake this bottle, is there any heat transfer associated with this bottle? No, right? It is adiabatic, perfectly insulated. But there will be irreversibilities, right? Correct? Hmm?
Okay, sir. Okay, sir.
Okay. So when you solve the questions related to turbine and this compressors, it is usually written isentropic process, and you assume that the process is reversible adiabatic because you don't know how much irreversible. Sorry, if you assume other way around, if you assume that it is irreversible plus non-adiabatic, then you will have to calculate amount of heat transfer. How much is the entropy generated? But you don't have the data in that question, right? So you assume that if the data is not given, then it should be reversible adiabatic. So that's why I'm saying that context will make it clear whether you have to go with the case 1. Okay, so there are two cases, whether you have to go with case 1 or case 2. Okay, whenever it is written asentropic process, it can be either reversible plus adiabatic or it can be case 2 irreversible plus adiabatic, non-adiabatic. You'll have to proceed with a single case, either case 1 or case 2. Okay, both are completely different. Okay, so which case you have to consider if it is written isentropic process, that will be made clear from the context. Okay. Okay, I
Okay,
hope
sir.
this is clear, huh? But in interview or somewhere else it is asked, then you should have a understanding that isentropic processes can also be irreversible plus non-adiabatic. Up question number 9. It is saying that an irreversible adiabatic process. Irreversible means entropy generation. Adiabatic means there is no heat transfer. So there is no entropy exchange between system and surrounding. Okay. So whatever entropy is generated, that will result in increase in the entropy of the system. Anyways, must necessarily be non-isentropic and will invariably result in a temperature increase for a closed system. So there are two things. One is that it will be a non-isentropic and it will increase the temperature. Okay, so you have irreversible plus adiabatic. Okay, so that means entropy generation is positive and entropy transfer is 0. So the total entropy change will be positive. Okay, so this means non-isentropic. What about temperature? What about temperature? So if the process is adiabatic, so that means heat will neither go inside the system nor it will leave the system. But if the process is irreversible, that means some high quality energy, some high grade energy is being degraded into low grade energy, into heat. Okay, so there will be some dissipations in the form of friction, in the form of viscosity, like that. Okay, so temperature will increase. ये जो example, for example, this example of this water bottle I given, a perfectly insulated water bottle I given. If you are shaking this bottle, then what is happening? There will be some viscosity inside the water, right? So because of that viscosity, whatever heat you, whatever energy you are providing in the form of shaking, you are shaking the bottle, you are providing some energy, some work transfer. That work transfer will be dissipated as heat. Why dissipation? Because there is friction, because there is
Hello, hello.
hello. Sorry, there was some connection loss. Can you hear me? Hello. Am I still audible?
Yeah, you are audible, sir.
Okay. So when we are shaking the bottle, basically we are providing some energy in the form of work, and that energy is being dissipated in the form of heat. Okay, and that heat cannot go outside the system because the system is adiabatic. Okay, so since that heat cannot go outside and work is continuously being converted into heat, so the temperature will increase. Okay, so temperature will increase. Okay, work or high grade energy will be degraded into heat. So the temperature will increase. Okay, so this is true. This statement is true. Okay, I hope this is clear. Now,
Sir, here,
uh-huh.
sir, again I am asking here, sir, why don't the
Mhm.
irreversibility of the adiabatic process doesn't make it non-adiabatic?
Because adiabatic or being non-adiabatic simply is about the boundaries. Okay, whether a system has adiabatic boundaries or non-adiabatic boundaries. So if the boundaries are non-adiabatic, they are perfectly insulated, then heat transfer cannot take place. Okay, but reversibility or irreversibility is independent of your boundaries, right? You can have perfectly insulated boundaries of your system, but irreversibilities can be there. Okay, right?
Yes, sir.
whether a system has adiabatic boundaries or non-adiabatic boundaries, that is independent of the process under which system is going on. Okay.
Okay, sir.
Now coming to the next question. Question number 10. It is saying that for an ideal gas with constant specific heats, the entropy changes as a function of temperature and volume is given by the exact equation delta S is equal to n times integration from Ti to Tif of Cv dt by T plus something. So you remember the formula? What should be the what we should fill in the blanks?
Is it like a VDP? We have to integrate VDP and write it.
Huh?
VDP. We have to integrate VDP and write, I think.
Okay, let's do it. How should I proceed? We'll have to start with the first law of thermodynamics. Del Q is equal to del U plus PdV. Okay. TdS is equal to du plus PdV, right? So you have ds is equal to du by T plus P by T dV. Okay. You can write what you can write for du. You can write Cv dt, right? So Cv dt by T plus, now again you have dV. So for an it is written ideal gas. For ideal gas, you have PV is equal to nRT. Okay. Hello. Hello. So you
Yes,
can
sir. Yes,
write P. So you can write P is equal to nRT by V. So P is equal to nRT by V. Then dV by T. So the T will cancel out. And if you integrate this, yes, if you integrate this, so it will become Cv ln T और लिमिट लगेगी है ना. So ln T2 minus ln T2. Okay, ln T2 minus ln T1, right? Plus n R and ln. Okay, we have to compare with this. So I should not have taken the Cv out because it may be dependent on the temperature. Okay, so it may be dependent on the temperature. I should integrate it like that. Okay, so n it is taken out, it is constant. Cv and dt by T, right? Integrate from Ti to Tf. Correct. I am just integrating. I am just integrating this thing. Okay. Plus integration of this nr and dv by v, integration from vi to vf. Okay. And it is given what it is. What is given? This is given. Okay. So we have to compare with this. Delta S is equal to n Ti Tf Cv dt by T plus this fill in the blanks. So now tell what is there should be in the fill in the blanks. This quantity, right? Correct. This quantity will be equal to nR ln V2 by V1, right? Okay, so like that you can calculate change in entropy.
So
I
here
hope-
we are getting this another extra answer,
Extra what?
extra n, small n.
Oh, sorry. Huh. Okay, so actually this d small u is equal to CVDT. Okay, internal energy per unit mass is CVDT, but here we are writing capital U. So d capital U will be equal to this number of moles times. Okay, so n will be there. Not the mass, not per unit mass, but per unit mole. It is just extensive and inextensive form. Okay.
Okay, sir.
Okay, so यहाँ पर n आ गया ये. So n, if this was small u, then no n, but we are writing capital U. Okay. Now question number 11. It says which of the following TDS equations is universally applicable for any process, whether it is reversible process or irreversible process, between two equilibrium states of a pure simple compressible substance. Option A, TDS is equal to du minus PdV. ds is equal to TDS plus VdP. TDS is equal to dH minus VdP. TDS is equal to CPdt minus VdP. Which one of these is correct for all?
So option B is correct, right?
Option
Option B.
Option B is correct. Okay. Why other options are not correct? Because they are not correct. But if option A was TDS equal to du plus PdV, then this would also have been correct. Okay. Right? But it is negative sign there. We should discuss, have a discussion on this question a little bit. Let us start with the first law of thermodynamics. First law of thermodynamics says that heat transfer dq is equal to du, change in internal energy, plus work interaction, right? Then for reversible processes, this del q is TDS. Okay, and reversible process of a simple compressible system, del W is equal to PdV. So you write TDS is equal to du plus PdV. Okay, so step by step, if you see, then it will be TDS equal to del U plus del W. Okay, or here you can write del Q. Anyways, so what I am trying to emphasize is that if you start with the first law of thermodynamics and you want to reach here, and if you are using these two assumptions in between, that the process has to be reversible, process has to be reversible, but when you reach to the final expression, you have removed both of these assumptions. Is that clear? What usually happens that if you have a equation, let us say you have some equation A, okay, with assumption 1, okay, you do some modifications assuming something else as well. Okay, so you add one more assumption and you get equation B. Then in equation B, you will have to say that both of these assumptions has to be true. Is that right? This is usually what happens, is right? You have some equation, and that equation is valid under some assumptions. Okay, then you assume some more, then you apply some more assumptions. Okay, and you get some new equation. Then that new equation will be valid under all the assumptions you have made earlier. Is that right? You're getting what I'm trying to convey?
Yes, sir. Yes, sir.
Okay, you are adding more and more assumptions, then all those assumptions should be there, only then the final equation will be valid. But here what is happening? Here you have some equation del q is equal to du plus del w, and you added this assumption that process is reversible, so you replace this dq by tds. You added one more assumption that process is reversible and a simple compressible system. Then you can replace del w by pdv, and you get the final equation. Then in the final equation, usually using this particular analogy, you can think that this final equation should also be having these particular two assumptions. Okay, that process has to be reversible and simple compressible system, right? This will come into our mind. But this equation is valid for all the processes, for reversible as well as irreversible. Okay, so this is a very interesting point. We reached this equation. Okay, so this was equation A, and this is equation B. We reached from equation A to equation B, and in between we assume we have taken two assumptions. But the final equation B, that is valid in general. For that we don't need any assumption. So this is very interesting. Why it is like that? So it is valid for reversible as well as irreversible. So this is valid for reversible and irreversible both. Why it is valid for all the type of processes? It is not depending on the process. It is depending on the points. Okay, so this is the important point. It does not depend on the path. It depends only on the points. Why? Because all the variables involved in the final equation B are the point functions. Temperature, it is a point function, right? Temperature is a point function. Entropy, again a point function. Internal energy, again a point function. It is a property. Pressure, again thermodynamic property. It is a point function. Volume, again it is a point function. It is a thermodynamic property. Okay. So all the variables involved in the final equation B are the point functions. So this equation has to be valid for all. For this equation, we need only the final and initial point. In between, what is happening, whether the process was reversible or irreversible, that doesn't matter. Okay. So for that reason, it is valid for all the processes. Okay. Similarly, in option B, we have entropy, point function. Sorry, temperature, point function, entropy, point function, enthalpy, again point function, because enthalpy is defined as internal energy plus PV, right? Plus V plus dP, right? Okay. I hope this is clear.
Yes, sir. Sir, how can we get to this option B, sir, with using this our equation?
With the equation, with equation B. Okay. So D. Okay. So H is equal to. Let me add one more page. H is equal to what? H is U plus PV, right? And DH, which DU plus PdV plus VdP, right?
Yes, sir.
So du is dh minus pdv minus vdp. And if you substitute du, this thing in equation B. What is equation B? Equation B is TdS is equal to du plus pdv, right? Du plus pdv. So in the place of du, you have to keep what? dh minus pdv minus vdp. Okay, then you have plus pdv. right, in equation B. So this PdV and PdV will cancel out, and you will be left with TdS is equal to dH minus VdP. Correct? Fine.
Yes, sir.
Okay, यहाँ पर माइनस है, सॉरी.
Plus.
Okay, so which option should be correct? Okay, so this is what du, everything is correct, right? This option, this is correct. dH we have differentiated, du is equal to dH minus PdV. Then we substituted this, du की जगह ये लिख दिया, ओ कैंसिल हो गया, तो dH minus VdP. तो dH minus VdP कहाँ है? तो ऑप्शन सी में है dH minus VdP. Okay, now correct. Okay, the T is point function, entropy is point function, entropy is point function, V is point function, P is point function. All these variables are point function. So this will depend only on the initial and final points, not the process in between. So it is valid for reversible as well as irreversible processes. Okay.
Okay, sir.
Okay. Now it is saying that we have to discuss the significance of general TS equations. Sorry, TDS equations. TDS equations drive how the equation TDS is equal to du plus PdV can be adapted for an incompressible solid or liquid to find the specific entropy change strictly as a function of temperature. Okay, significance you have already seen. Okay, significance you have already seen that if you have TDS equations, okay, for example, in the case of this ideal gas, you had the TDS equation, and from the TDS equation itself, you got the formula for the change in entropy. Okay, so that is the significance. You can calculate the entropy change. Okay, now it is saying which type of processes for an incompressible solid or liquid. Okay, question number 12, it is saying for a incompressible solid or liquid. So in case of solid or liquid, the volume will remain constant, right? Incompressible. Hello?
Yes,
Hello?
sir.
So for incompressible, solid or liquid, this dV will be 0. Okay, so the TDS will be left with du, right? Because PdV in the PdV, this term will be 0. So ds is du by T, right? Hello?
Yes, sir.
So ds you can write CVT by T, and you can calculate the change. Okay, S2 minus S1 will be integration, and CV dt by T from T initial to T final, right? If the CV is constant, if this specific heat is constant, then you can take out from the integration as a constant. But in some cases, it can be the function of temperature. So this can be the function of temperature. Then you cannot take this outside. Okay. Then you will have to use how this is dependent on temperature. Okay. You will have a expression how it is dependent on temperature. Okay. Usually you can approximate this relation between CV and temperature using some polynomial. Okay. You can use the CV is equal to like some constant C0 plus C1T plus C2T square plus C3T cube, like that. Okay, and these value are usually listed in some tables. Okay, anyways, so this is the function of temperature only, right? The CV is the function of temperature, and in the denominator also we have temperature, and we are integrating with respect to temperature. So this whole quantity, so the whole change in entropy will be the function of temperature only. Okay, so that's what we had to derive how this equation can be used to strictly find this entropy change strictly as a function of temperature. So we have a function of temperature here. Okay, So I hope that is clear. Now coming to the next question, question number 13. It is saying when plotting the states of a pure compressible substance, there are some diagrams. We have to tell which type of diagram, also known as enthalpy entropy diagram, is particularly useful for visualizing the critical point and constant pressure temperature lines in two phase and superheated regions. So, you have already discussed, studied this in basic thermodynamics course. This is
Module
called
chart.
Module charts. Okay. Okay. Now coming to the next question. Question number 14. It is saying that an isentropic process for an ideal gas. Again, isentropic means entropy change is 0. For an ideal gas can be modeled and mathematically as polytropic process. Now, we will returning to that point. We have discussed that isentropic process can either be reversible adiabatic or irreversible non-adiabatic with heat loss. It is saying isentropic. It is not telling us whether it is reversible or irreversible. We will assume here that this is irreversible adiabatic. Sorry, reversible. If we assume that it is reversible, so it has to be adiabatic. So PV to the power n is equal to C. That means n has to be Cp by Cv. This is case 1. If this was case 2, if this was case 2, then there will be something else. Okay. But if you assume that process is reversible, then it will have to be adiabatic. In that case, this power of volume has to be the specific heat ratio. Okay. Now coming to the next question.
Sir, one doubt in last question.
Hmm.
But question does not say no, it is a reversible process.
It can be a reversible process. It can be an irreversible process. In that case, this may not be valid. But it is saying that it is mathematically modeled as polytropic process. PV is equal to C, PV to the power n is equal to C. What should be the value of polytropic index n? So if this is not reversible, then we should know how much is the irreversibility involved. Okay. If we know how much is the irreversibility involved, what is the entropy generation? Okay, how much is the entropy involved? How much is the irreversibility involved? That is quantified by entropy generation. Okay, so if you had entropy generation, then you can calculate what should be the heat loss, so that entropy generated can be compensated with the entropy, entropy going out from the system. Okay, but you don't have the amount of irreversibility, you don't have the amount of entropy generated in the question. Okay, so there are two cases only, as we discussed, for isentropic process. One is reversible adiabatic, another is irreversible non-adiabatic. So if we go to this case, then option C is correct. But if you want to go on another case, then you should know the exact amount of entropy generation. Okay. But we don't have the amount of entropy generation. It is not given in the question how much entropy is generated. And usually I said that context made it clear. So as per my assessment, since entropy generation is not given, the amount of irreversibility is not given, so I will go with the case 1. Okay. Similar
Okay,
thing
so
you will.
yeah, so in the other way, I can say that option A, B, and D are correct for an irreversible process.
But
May be correct.
they
May be
may
correct.
they may be correct. they may be correct if you know exact amount of irreversibility involved. Conceptually, yes, they may be correct. But I'm not sure that whether such type of processes can have this type of form or not. It is clearly written that this process has this type of form. And we need to check one more fact here that can discuss in the next class. Are all processes having the form PV to the power n is equal to constant reversible? Okay, that we should discuss. But in this question, I will go with the case 1 because entropy generation amount is not given. And again, I will highlight the fact that usually you encounter these type of questions for case of turbines and compressors, where it will be written that assume a isentropic compressor, isentropic turbine. In those cases also, you'll have to assume it is reversible IDFT. Okay. Now coming to the question number 15. It is saying that entropy change of a closed system can never be negative. Okay. Entropy change of a closed system can never be negative because entropy production must always be greater than or equal to 0. Now we have to tell whether this statement was true or not, true or false. Hello? It is true or false?
Yeah, it is true.
It is true. It is closed system. Closed system means there is no mass transfer, but heat transfer can be there. Closed system means it is saying that entropy change of a closed system can never be negative. Entropy change of a closed system can never be negative, but closed system can have heat transfer. And if that closed system is continuously losing heat and it has lost so much heat that it can make the entropy change negative. Okay.
Yes, sir. True. Yeah, true.
Yes. No, false, not true.
Yeah, what you told is correct.
So entropy change of a closed system can be negative because there can be, lot of heat losses. But if it was a isolated system, then isolated system has neither the mass transfer nor the heat transfer. So in that case, there will be no entropy exchange because of heat. So there will be either entropy change will be either 0 or positive. Okay. So in that case, it would have been true. But for a closed system, it is false. Okay. So we have more questions, I think, but we are running out of time. I had many questions but today we have like good discussion, so we could not solve these questions, but I will upload this, whole PDF, and you can try to solve the remaining questions. And if you face any difficulty, any doubt, then definitely we will discuss in the next session. Okay. So should we stop here or we need to discuss something else? Is everything we discussed in this session is clear?
Yes, sir.
Okay. So I will upload this PDF and you can try to solve the remaining questions. And if you have any doubt, we will discuss in the next session. Okay, we will stop here. Thank you for joining. Take care. We'll meet on next Tuesday.
Thank you, sir.
Okay,
Sir,
thank
at
you, sir.
last, sir,
Yes.
can you just tell the comprehensive in a comprehensive word, sir? I'm not able to differentiate between irreversible adiabatic and reversible adiabatic.
Okay.
I thought, sir, reversibility of the system will make the process adiabatic to the non-adiabatic.
There are two different things. Adiabatic simply means there is no heat transfer. Okay.
Yes, sir.
And reversibility or irreversibility, that is independent of the boundaries. Okay.
Independent of the process.
No. Process has to be either reversible or irreversible. Okay.
Yes, sir.
A adiabatic process simply means there is no heat transfer.
Yes, sir. No heat transfer.
And simply there is no heat transfer, then the entropy exchange that is associated with the heat transfer, entropy transfer through the boundary. How much entropy transfer is there through the boundary? That is dq by t. Okay, that is through the boundary. Okay, but the total entropy change is whatever entropy change is because of entropy transfer through the boundary plus entropy generation inside the system itself. Okay, the entropy change means total entropy change, that is entropy generation inside the system because of irreversibilities plus the entropy exchange through the boundaries. Okay, if the process is if the system is adiabatic, that simply means that there is no entropy exchange through the boundaries, but there can be entropy generation inside the system. Okay.
Yes, sir.
So reversibility or irreversibility means what is going on inside the system. Okay, when we say internally reversible or internally irreversible, then we are saying what is happening inside the system. Inside the system, if the entropy is generated, then it is irreversible. If inside the system entropy is not generated, it is reversible. Now moving to the boundaries. If there is no heat transfer through the boundaries, if the system has adiabatic boundaries, then there is no entropy exchange through the boundaries. But entropy can be generated inside the system or it cannot be generated inside the system, depending on whether the process is reversible or irreversible. Okay. When we say reversible or irreversible, usually we are referring to internal irreversibility or internal irreversibility. Okay. So this internal irreversibility or internal reversibility is about what is happening inside the system. And adiabatic means what is happening at the boundaries. Now is it clear? They're two separate things. Okay.
Okay, sir. Okay, understood, sir.
Okay. If there is any doubt, then we should discuss in detail. And today I think we are already out of time. We can discuss it in the next section. And if you have any doubt, then we should have a detailed discussion. Okay. But I hope this is clear that internally reversible or internally irreversible basically means what is happening inside the system, right? Reversible means no entropy generation inside the system. Internally irreversible means entropy generation inside the system. And adiabatic means at the boundaries. At the boundaries, heat is being transferred or not. If heat is being transferred, then there will be some entropy transfer associated with the heat at the boundaries. Okay.
Okay, sir.
Now is it clear or?
Yes, sir. Clear, sir. Understood, sir.
Okay. So an isentropic process can be reversible plus adiabatic, or it can be irreversible plus non-adiabatic. Non-adiabatic in such a case that heat should go out from the system in such a amount that the entropy generated inside should be compensated by the entropy going outside associated with the heat. Okay. Okay.
Yes, sir.
Okay. Okay. Thank you. Just try to solve the remaining questions. And if you face any difficulty, then we will discuss in the next session. Okay. Thank you for joining. Take care. We will meet on next Tuesday.
Okay, thank you.
Okay. Bye.